I'm happy to dive in. Yeah, for sure.
Okay, let's make it happen.
Well, welcome everybody. Excited to be here for the session 3 of the RAINA RDH Deep Dive into Rainscreen series. My name is Todd Kimmel. I'm co-founder and chairperson for the Rainscreen Association in North America, and I'm excited to be part of just kind of the introduction process here with Dr. Straub. I'm going to hand the mic, so to speak, over to him here in just a minute. I'm venturing to guess that many of you were on our previous program, so we're excited to kind of take this next step. And I don't want to be redundant, but I do want to kind of share a few words about the Rainscreen Association. We are a relatively new organization founded in 2020. Our focus is on kind of bringing the industry together to kind of create a level of consensus and support for performance-based criteria around best practice Rainscreen. And so we are a very active and dynamic organization that is kind of a committee-based organization around Rainscreen performance, around education and training, around building codes, definitions. We just launched a whole committee dedicated to retrofit, as we're seeing a lot more retrofit with Rainscreen coming about. And so this association is not just a manufacturer association. It's made up of the likes of architects, enclosure consultants, contractors, other trade associations, to really have a well-rounded vision on this. And we're excited, obviously, to have RDH as a very active member organization. And you can go to the next slide, John. I'm just going to talk a little bit through this. And so we definitely, if you're not a member or if you're interested in becoming a member, please look into this. There's a lot of opportunities to kind of grow and influence the industry and to push things forward on best practice. You can go ahead, John. And so, there's going to be more information on how to join later on. And certainly we are recording this presentation and it will be accessible in the future. So if you guys don't want to take notes, you'll be able to access this again. And John will show you how once we get to the end. But here's some more information on just QR code to get more involved in RAINA. But I think without further ado, I'm going to hand it over to John. If you guys have questions, please enter them into the Q&A portion of this presentation. We'll be monitoring that and collecting those questions at the end. If there's any sort of programmatic challenges that you have, please put that into the chat, and the administration here will be able to address some of those things as we go. But without further ado, John, I'll hand it over to you.
All right. That even rhymes. You're such a poet there, Todd. Yeah.
I'll try.
So as I always, this is session 5, which is quite remarkable, actually. And Graham Finch did the introductory one, and then I've done 3 here that are kind of more nerdy. The scientific background, then drainage, and today I'm going to do ventilation. But luckily, Graham will be back next session to drive into the water resistive barrier part of Rainscreens. And that's why I want to start here every time with just reminding everyone that Rainscreens are one of the 3 available strategies for rain penetration control in walls, roofs, below grade. And the other, the oldest one, of course, Pyramid of Giza, old masonry buildings in Europe and North America would use the mass approach. We also still use the second approach, labeled number 2 here, the perfect barrier approach, whether that perfect barrier is concealed or exposed, a face sealed system. Those are widely used in roofs, below grade water proofing systems, etc. So, but today we're going to be focusing, of course, on Rainscreens. And Rainscreens have a number of features that we have to look at individually to be able to understand them better and to be able to specify and construct and inspect them. So the reason people are very interested in Rainscreens and why the market has shifted strongly in the last 50 years, and it's been 50 years, towards Rainscreens, is that rain penetration and moisture management, like condensation, are major concerns in building enclosures, both the design, construction, and operation. Rainscreens as a concept offer excellent performance. Theoretically, from a building science perspective, they have all of the things right. And lightweight cladding systems like thin cladding types, whether they be ACM, fiber cement, high pressure laminate, terracotta, all of them lend themselves to a rain screen application. And it is also these types of cladding systems which have become quite popular amongst in the industry. So let's now start with one of the committee outcomes that Todd mentioned is that RAINA has a rain screen definition committee. And this committee defines a bunch of terms to try and clear up confusion in the industry. And rain screen is defined as an assembly applied to an exterior wall, which consists of, at minimum, an outer layer, an inner layer, and a cavity between them sufficient for the passive removal of liquid water and water vapor. Quite a general and broad, and I want to be a little bit more practical about it. And today we're going to focus on that cavity and the passive removal of water vapor. The last session was the cavity and the passive removal of liquid water. The next session will be the cavity and the liquid water and and that inner layer that does that. So this is what a typical rain screen wall system would look like. And I'm making it more real because I'm now adding what the structure backup is. A rain screen doesn't include the steel studs, wood studs, CMU, or cast in place concrete, which is the structure and backup. And it also doesn't include exterior continuous insulation. But modern building assemblies routinely have those types of features. What it does include is that cladding, the gap, the water resistive barrier on the inside, and also weep holes and drain openings. So with respect to focusing on ventilation today, the first thing is like, what is ventilation? Well, it's the intentional flow of outdoor air behind the cladding. And the reason why we would do this is generally two reasons. One is to bypass the vapor resistance of the cladding to limit condensation in general. But also we want to allow drying of moisture that might be in the backup wall or within that cavity or even within the back side of the cladding. So those are connected items that we're going to dig into. That's why we ventilate. What you'll notice is not in this list is cooling. There is, amongst some areas, there's some real misunderstanding that providing ventilation behind the cladding in a wall system will provide meaningful cooling. And that is an answer that we know the answer to that question. It doesn't. There is almost no benefit in a modern wall system to providing ventilation in terms of reducing the temperature that the cladding sees or that the overall wall system sees. Air does not have a great capacity to store heat. And that means that to remove the heat under solar conditions, when we are getting hundreds of BTUs per square foot per hour delivered, or 500 watts per square meter delivered, you would need airflow that is way higher than is practical to achieve. And that's why airflow just doesn't provide much benefit. So we can take that one off the table. I think that's pretty unequivocal by any science that the temperature differences are a degree or two if you really ventilate a lot. But air does have the ability to store meaningful quantities of water vapor. And that amount of water vapor is aligned fairly well with the kind of moisture levels that we might want to remove from a cladding or a cavity. But that's limited too. Wall ventilation can only remove a certain amount of water measured in the ounces per day in a sort of 10-foot length of wall. It's not gallons per day. And so we still need to focus on drainage as the primary mechanism to remove, say, significant quantities of water because of rain penetration. but we also still need ventilation to remove the leftover water droplets and wetted materials that remain in an assembly after drainage has stopped. So, as a sort of a counter example, just take a look at this metal clad wall system here. That sheet metal is, I think everyone knows, a perfect vapor barrier. It has a zero perm rating no matter what units you use. And I've even made sure that I've chosen a photo where the corrugations are horizontal. When you use a system like this in a cold weather conditions, condensation is going to occur on the back of that metal cladding because it's a vapor barrier on the cold side and condensation will occur. This may even build up as frost if the temperature is below freezing. However, this doesn't usually cause too many problems if it's not too much because, a sunny day returns, the frost melts, and the water, the condensate will run down the back of that cladding. And provided you have a drained system, which these systems are designed or should be designed as, then the water weeps out the bottom and you don't have a problem. Now, it would be better to ventilate this system to allow outdoor air to flow behind it, because then rather than having to have that water drain down and leaving water behind clung to the surface, we could dry it out when the sun came out. And that by drying it would reduce the time of wetness that the back of the cladding experienced. So let's dig in a little bit more into this why ventilate. And ventilation, as it's shown here, I'm showing air going in bottom holes or slots, passing behind the cladding and going out the holes or slots at the top. Notice, of course, that any interruptions in the cavity, we need to provide a path for the air to flow through or around. So in this case, I've shown vents below the windows, but it's also quite possible to let the air flow laterally around the window as well. So with a system that is vented, you would have only openings at the bottom. That's the image at the right. When you have a system that's ventilated, you have openings at the top and the bottom. And that allows that airflow arrow that I drew in this example to occur. Ventilation is flowing through the cavity. That can occur in the design on the left, and it's very difficult to occur with the design on the right-hand side. That doesn't mean that some outdoor air doesn't get into that space. It will, depending on the gusting of the wind and changing temperatures, but the amount of air will be much, much less on the right side in the vented system versus the left side. As I've stated, all these Rainscreen systems are first and foremost drained systems. So both of these wall systems, vented or ventilated, have a water resistant barrier, have flashings that collect the water and direct it to the outside through weep holes. The difference is there are vents that are over the whole cavity, typically the top and the bottom of a ventilated system. There's no firm scientific definition that could say, how do I measure whether something's vented or ventilated? But usually the telltale sign is that you have a decent sized cavity over 10 or so millimeters in size, over 3/8 of an inch, and you have vents that are at the top and the bottom. Now, historically, in Europe, they came up with this idea of a back ventilated wall system on the left-hand side. This is from a 1988 UK publication called Rainscreen Cladding, so kind of relevant. And their assumption was that there was vents were at the bottom and at the top, that there was a water barrier but no air barrier, which is not true today. And also that you could have multiple vents spread through the cavity. You can see there's one in the middle at the top, whatever. On the right-hand side, they had what they called a pressure equalized rain screen. And this was different because it didn't have vents at the top and the bottom. It just had vents at the bottom. And also, it didn't have a water barrier, it just had an air barrier, and it compartmentalized. I'm going to return to that very special subset of pressure equalization at the end of this presentation today, because most of what I want to talk about is about ventilation first, and that is a much broader category of enclosure wall system. Now here I'm just showing you a mock-up. I thought I'd throw a photograph in of a drained and vented system. This system is, bent metal panels attached to a very clear water resistive barrier. The venting and draining occurs through just holes drilled in the bottom of the panels, and relatively small one, 3/16 by 3/4 inch slots, two per panel, are provided, which is quite sufficient to let rainwater out. And it does let a little bit of air in, but there's clearly no easy path for air to circulate behind this cladding in and out. So this is quite a reasonable wall design. It's just that it would not have as much ability to dry out moisture, to deal with condensation, etc. It wouldn't have a problem with rain penetration performance, but if you put it in very humid, challenging exposures and uses, or made the cladding out of a material that was corrosion sensitive, you would have less performance than if you ventilated it as well. Another sort of example that is worth thinking about is lap siding ventilated? When we deal with lap siding, and of course these are all residential low-rise examples, where we don't have deliberate vent openings in most cases. We're just relying on imprecisions in the lapping to allow water to come out and to allow air to go in. Now, in some systems, though, that is quite limited. And if you take a look at the wood, the modern, nicely planed and cut wood lap siding on the right-hand side, that system, if you paint it with a thick paint or paint it several times and build up a thick layer, it will have a problem both letting rainwater out, although that usually happens through the smallest of gaps, but it certainly won't allow air behind it. Whereas even if you tried to make a vinyl siding airtight, there are so many loose gaps and joints that when that product is measured, which has been done by several people, you really notice how well ventilated it is, because it's hollow behind that vinyl siding, built-in cavity, and there are lots of open gaps. So this distinction where I'm saying vent opening at the bottom and the top and a clear cavity is the obvious one, and the one that applies to a lot of commercial institutional type buildings, but there are lots of cases where it's not quite as clear cut. So a lot of what I'm going to be telling you about today is based on a pretty strong history of research. And so cladding and ventilating cladding has been something that's been talked about in serious scientific circles for decades. And several large projects have been undertaken, and this is an active area of research, especially in Europe, where, again, they've been moving from the mass type systems to the cladding systems over the last few decades, and so working on things like drainage and ventilation. In North America, a number of these projects, these papers in North America and research are from the early 2000s. In New Zealand, there was a lot of work done, which I will refer to later, in the mid 2000s to the end of 2000s. And then now in the last, since 2012, 2015, there's a lot more research being done in Europe. So it's not like we don't have a good understanding. The basic physics of this has been written down in textbooks that go back to the 50s and 60s. And I'll show you a really good set of texts that was from the 70s in a bit. But in North America, CMHC did a study in the mid 1990s, Canada Mortgage and Housing Corporation, which is available online. And then ASHRAE supported a project I'll tell you a bit more about to understand this. So what the two graphics on this screen are showing is on the left-hand side, we're saying that the air flows in a particular path. And the example shown, the path is A to B, then B to C, and then C to D. Now, it could go in the reverse direction. It could go D to C and B to A. But there is a flow path to provide ventilation flow. The importance between identifying these different areas is that A to B is governed by the airflow through the vent openings, the weep holes, the open joints, the slots. The flow from B to C is defined by what the cavity is like. And you can't talk about ventilated wall systems without talking about both of those components. You have to know how the air gets in and out, that would be the vents, and you have to know how the air flows in the cavity. In some systems, the cavity is the limiting factor. In many systems, it is the vent that is the limiting factor. So on the right-hand side drawing, I'm showing the equation you would use to calculate the pressure that drives airflow through the cavity because of or when the cavity temperature is different than the outdoor temperature. And the cavity temperature is often very different when the sun heats the wall. So the sun heating the wall will often show that the cavity gets to 20, 30, 40 degrees warmer than the outdoor air temperature in bright sunshine. And that really matters to driving ventilation flow, and it also helps a lot for drying. So while I'm mentioning the solar buoyancy, the other force that drives airflow, ventilation airflow behind wall claddings is wind. And I'm going to show you some images of wind pressures. This is from a German study in northern Germany on a multi-story building, 20-story apartment building with panel cladding from 1973. So while I was toddling around, I guess I just got out of diapers. They were measuring the velocity of airflow behind panel cladding systems in apartment buildings. And what this is just it's a whole PhD thesis, but there's a bunch of results here showing the velocity on both the windward side and the leeward side. And the airflows that they're measuring in this panel cladding, open jointed panel cladding, are quite generous, with flows in this range. 0.2 meters per second is a little under 1 foot per second, and 0.4 is a little over 1 foot per second. So you can see that the air is moving at pretty good rate through this panel cladding with an open cavity and good joints. So we know that it can actually move a lot. And some of this stuff was written down in books in the 80s. This is a German book, obviously by a person named Leosch. There's actually multiple volumes. Bunt is volume 1, is like Vorhangfassaden is just German for these panel claddings that are hung on the front. And a lot of theory was provided as to calculating the cooling effect, the ability to remove moisture, and very little measurements, but there was a few things. This is also from the late 70s, from the Fraunhofer Institute, the people who brought you WUFI. In fact, the author of WUFI's was a guy by the name of Hartwig Kunzel, and it was his father who did this research. And this was an example of wall system number 1, where they had small shingle type claddings that were glued to the wet masonry wall. And then wall number 2, they put them over a 3/8 inch furring strips and allowed openings at the top and the bottom. And they measured by literally coring out the masonry. They measured the moisture content in two different walls over a period of over 2 years. And it was pretty clear to say ventilated systems allowed much faster drying of this wet masonry than if it were not ventilated. So this was the start of actually measuring the impact of drying. But although these were indicative and the theory suggested it, certainly in North America, there was not a lot of good understanding. And one could argue that the understanding is now reserved to a small scientific core. But in the time period, starting in 1999, a major multi institution research project was undertaken. It was Research Project 1091 that investigated the impacts of air gaps, of ventilation, of venting, of different types of cladding systems. And as part of that, I was involved doing a field study of drying rates. And here you see there's 5 different walls being built in a test building, and several of them are they're identical except that they have vents at the top and the bottom in a brick wall. So the vents are only open head joints, so not a lot. Every 2 feet, one head joint was left open at the bottom or the top. And one of the things, these are some results from that type of study where I'm highlighting for you the vented brick wall versus the ventilated brick wall. And we would dose water into not the back of the cladding, but the sheathing of these framed wall systems. And that was so that we could measure exactly how much water we added, which turned out to be 1.8 kilograms. That's about 2 quarts of water would be added. And then we would watch by measuring the moisture content of various parts as the wall dried down. And it was pretty clear that identical walls that were ventilated were much better drying than walls that were unvented. Or sorry, were vented but not at the top. So just we didn't even bother trying to not put vents in the bottom. We knew that that would be a bad idea. So although this is just an evocative examples again, it was used to run computer models to learn what does it take to predict these performance curves of wetting and drying and wetting and drying. And that confirmed that the physics that we understood about how to predict both ventilation flow and the drying effect of that flow were reasonably predictable. None of this stuff is very precise, but it is now, I would say, more than precise enough to make quite useful design decisions. Following up on that, the Building Research Association of New Zealand did a lot of really good work of using predictions, measuring actual ventilation in walls. And here's one of the results that they had of the drying time per gram of moisture. Now, there's 28 grams in an ounce for those people who think better in ounces. So how many hours to dry a gram is on the left axis. And they measured 4 walls of different cladding types that were drained and ventilated. They measured 3 walls that were drained and vented. And the vents, there was no vents at the top, but it was kind of air leaky at the top. And then they had 4 walls where they had the cladding attached directly to the water resistant barrier. And those are the drain direct fixed on the right-hand side. And so it was pretty clear that the drained and ventilated walls were about 3 times faster drying than the direct fixed. And that was, again, based on measuring the moisture content of materials after inserting a known quantity of water to represent a failure, a gap. Okay, so I would say that what I would like you to take away from that is that we do know that ventilation can remove moisture. We can even quantify to a fair degree of certainty how much moisture can be removed. And we know that the amount of ventilation in normal walls doesn't make a difference from removing heat flow. It doesn't change, it doesn't cool down a wall, even though it may, you may think it does. The science would say not for walls, it doesn't. So, how much ventilation do we need? And Todd and I were talking about this at the beginning. Well, how much ventilation you need depends on the building's exposure to rain and sun, the materials that you make your assembly out of, the design of the assembly. Are you actually have a WRB over, say, wood sheathing, or do you have insulation and then a WRB over gypsum sheathing? Makes a big difference about how much ventilation you need. And also your performance expectations. Are you looking for a design life of 200 years? Are you looking for a design life of 40 years? You know, you're going to get different answers. But to try and summarize what we know from trying out all these different scenarios, it doesn't take very much ventilation to bypass a vapor impermeable cladding like corrugated metal. It doesn't take many vent openings, and it doesn't take much of a gap. But it does take a fair amount of vent openings and a fair amount of gap to dry out significant quantities of either built-in construction moisture or rainwater. And interestingly, that when we move to having very open joints, one of the concerns is that those joints will allow a lot more water in, which is true, but it will also allow much more ventilation, and that ventilation drying maybe provides more drying than the additional wetting that the open joints get. That's sort of the balance that is in play when we're talking about all of these different systems, assemblies, different climate zones, and different expectations. So here's one part that we can write down in a rather quantitative and confident way. So this chart here is a chart in both metric and imperialistic units, where we have the flow rate for ventilation on the bottom per unit area. And on the vertical axis, we have what is the vapor permeance, and it's an equivalent vapor permeance. How much water vapor will move across that cladding depending on the difference in vapor content, and in this case, the flow rate. So the bottom line, this big straight line that's hopefully high glow green, is the line for a completely vapor impermeable cladding. As you increase the ventilation flow, you increase the ability for water vapor to go around that cladding. And if you're comfortable, say, with US units, the line here in the middle of the graph, mid height, is 1.75 US perms. And if you want to get to 2, 3, 4 perms as an exterior cladding, you'd need to ventilate at a rate of, well, something over 0.03, 0.05 CFM per square foot of wall area. So it's difficult to tell you how does this apply to your project without knowing all the specifics of your project. But I'll tell you that the amount of flow, airflow needed to achieve that is shown by, say, the big blue arrow. It actually is quite easy to get to these lower levels of airflow. And they will easily bypass the vapor barrier that is a glass, polycarbonate, ACM, Rainscreen type of a cladding. Now, not all claddings are completely vapor tight. And so as an example of something that's actually quite vapor open, I have a 90 millimeter brick veneer here shown in the reddish color. And basically, it doesn't need to be ventilated because diffusion will allow water vapor to go through it. Now, that said, if you do ventilate it, it starts to make a difference. And it not just allows water vapor to go through, effectively go through the brick or around the brick, really, but it'll also start to dry out some of the inside of the wall. And so that's why people are trying to add ventilation to brick, is that it will increase its effective vapor permeance by multiple times. But when it comes to things like steel and metal and plastics, adding ventilation is even a little bit is really important to deal with avoiding condensation. Now, we can calculate how much air flows behind a cladding if we know the pressure that is driving that airflow. And we can calculate with good degree of certainty the amount of pressure driving airflow behind cladding due to the sun. The wind is a lot more variable. As I showed you with those numbers, it does bounce around an awful lot. And while we can make some estimates, and they're usually good enough, it's really the sun that we tend to focus on in practice, because the sun is highly predictable, and it also occurs at a time when we were using that sun's energy to evaporate moisture. It's not just driving airflow, it's also evaporating water that might be in the cavity or adjoining the cavity. And that's why during those periods, you get lots of drying. Now, I've got 4 arbitrary walls labeled here, walls 1 through 4. And when I'm saying stucco Rainscreen and wood siding Rainscreen, what I mean is they are on 3/4 inch furring strips. And the assumption is that there's a 19 millimeter or 3/4 inch air gap. When we look at at very small pressures, and you'll notice the chart at the bottom, these are log charts, even at 1 Pascal, we get hundreds of air changes per hour of the air behind the cladding. And that amount of airflow is quite sufficient to move a fair bit of moisture. In those systems, it's really as much about whether we have the heat energy to evaporate water is more of a governing factor than whether we can get enough airflow through the assembly. Now, I want to point out here that wall number 4, which is the middle blue line, this is actually has a 2-inch air cavity, and we have vents at the top and we have the vents at the top and the bottom in the form of holes. And those holes are 3/8 by 1 inch, so a little larger than many of them. But it is the holes that is limiting the airflow. Nevertheless, even at pressures of, say, 1 to 2 pascals, which are very small pressures, we would expect air changes in the rate of 10 to 20 per hour. And that's more than enough to bypass the vapor resistance of the metal cladding system. The brick veneer is showing the least amount of ventilation flow in this example. And that's also what we measure in the field. And that's because the weep holes are not very large, and the cavity is often quite rough, and it resists airflow, easy airflow. And it tends to be smaller, under an inch, tends to have mortar dams and droppings. And that means that it tends to have the lowest type of airflow of these systems I'm comparing. And this can be calculated from a spreadsheet. You just need to know the information about what system you're using, and then you can figure out where your system will land. This is a results from a paper that my colleague Graham Finch and I produced. It's many years ago now. The research was done about 15 years ago, and the paper was published over 10 years ago. And what's being shown here is that we're calculating the effective ventilation rate in the dark blue line, as these are the measured results on the wall system. Were showing us the temperatures in the cavity, which allowed us to calculate the ventilation rate with good accuracy. And what's point out, this is a stucco Rainscreen on a 3/4 inch cavity. It doesn't have to be stucco. It could be a flat plate of metal or HPL over top of a 3/4 inch cavity. But what's key is that there is a continuous slot at the top and the bottom. And those continuous 1/2 inch slots allow air in and out quite easily. And as a consequence, if you look on the right-hand side, the blue is measuring air change rates of 100 to 3, peaking at 400 air changes an hour. And that is plenty of airflow to allow for drying and certainly bypassing any vapor resistance that the cladding would have. But this is what I would call a pretty well ventilated system because it has open vents at the top and the bottom that are essentially continuous. Now, back to New Zealand, they measured the ventilation rates in walls by using tracer gas studies. And this is a plot comparing the calculations to the measurements. And the calculation methodology we developed and published in the ASHRAE research project was shown here by other researchers on a whole range of different wall systems to be pretty accurate at predicting what they actually measured in terms of ventilation rate. So we have this, again, adds to our comfort that we can predict the airflow and we know how much airflow if you tell us about the system. This is, again, the drying rate measurements plot showing you in a different way. And what I want to point out in this assembly or this slide here is these different colors bands are different parts of the wall assembly. And the uppermost red is actually the wood framing in these assemblies. The wood framing showed the longest drying times. Ventilation has the least impact on drying out framing. But the bottom line, which is drying at literally 1,000 times faster, that yellow line here at the bottom, that grouping is the cladding itself. Ventilation has the biggest impact on drying out cladding, and the cladding dries out very quickly. Whereas framing, ventilation has little to no impact on drying out the wood framing. But it can have an effect, but it's not a big one. The big effect is the sheathing, which is the greenish lines here, and the cladding itself. So the idea behind Rainscreens is slowly working its way into our building code. This is a new IBC requirement, a few years old now, that for moist or marine climates, which are the left and the right side of the map, the marine, moist and marine, you are required to put in 3/16 of an inch of a gap behind stucco. And it is just stucco. It's not behind brick or whatever. And they've chosen 3/16. Now, this is a committee choice. So this is a pure compromise. There's some science. Most of this gap is probably to provide drainage. The code doesn't tell you these things. So you have to guess, and it results in myths and mistakes, actually. So the 3/16 inch, without a doubt, is more than sufficient to provide drainage. Is 3/16 enough for ventilation? Well, that depends more on the vent openings and the bottom of the top treatment than it does that 3/16 of an inch. So if all we provide are 1/2 inch weep holes at the bottom, then we're getting very little ventilation. If we have a continuous slot of 3/16 at the bottom of the top, then we may begin to see, even with this small of a cavity, some real benefits of ventilation to drying out the cladding and the sheathing. Now I'm going to show some real sizable ventilation gaps. So on the left-hand side, we're seeing vertical and horizontal wood furring strips to support an HPL cladding system. This is a very open cavity. However, the entry vent at the bottom and the exit, there's only one at the top and one at the bottom, and they are largely blocked by perforated screens, so they may not be that well ventilated. The system on the right is a combination of metal furring and wood furring, which is why I chose it. But I know the system on the left, it is completely open at the bottom. The cladding is attached and the bottom is open. And so it is well ventilated, open at the top and the bottom. Where we see intermediate solutions, we might see systems like this. These are, we see an increasing number of these ventilated or perforated furring strips or girts, depends what you want to call them, strapping, hat channels. And those holes definitely restrict airflow. The one on the left, which is intended for a roofing installation, doesn't restrict the airflow much. The one in the middle, a fair bit, because there's not that many holes. And on the right, still a fair bit. So, meaning by fair bit, I mean it restricts the airflow by several factors, 2-3 times, maybe 4 times less than if you didn't have a horizontal strip. Now, we are seeing a proliferation of ideas about how to ventilate both in the cavity. What concerns me is that the cavity is fairly understood and predictable, but we haven't actually been honest with the vent openings. The products in the middle of the screen, air gap membranes, entangled meshes is a generic terminology. These actually have an ASTM test standard for how you measure the airflow resistance of them. But it doesn't include the vents. And the vents are often going to be the dominant factor. So, how many vents? So, this is a cool building in New York City. Todd probably knows it. And when you look at it, you can see, I don't think there's a lot of problems with air getting through that cladding system. But of course, we also know that there's very little challenge with water getting through it either. So it's more of a screen, and it's so well vented and hence ventilated in the cavity behind. Water goes through, but so does air. This would be a more realistic open joint cladding system. I'm showing you a stone one on the left and a fiber cement one on the right. And these joints tend to be somewhere between 1/4 inch, maybe 3/8 of an inch, rarely wider, to try and limit UV and solar and water getting in. These are, however, highly ventilated. In these systems, really the airflow is only limited by what's going on in the cavity and what the forces are driving the airflow. But these are very well ventilated systems. You wouldn't really have to do much calculation. When I look at this system, these joints are not well ventilated. In fact, the joint themselves is completely blocked. And usually what we have is some form of weep holes being added every so often. And you'll notice at the top of this wall, it doesn't look like they're leaving the top of this wall open below that parapet. So this is a better example of a drawing that shows that they have weep holes. Now, are they weep holes? Yes. Are they vent holes? Well, yes, they will be that too. But notice that the weep holes are only at the bottom. There's none at the top. And so how much air is actually going into this system and moving around behind the cladding? Probably very little. Probably very little. And so it's hard to know that this system's performing very well as a ventilated system. It's quite likely not. Now, the hole, if you look on the bottom left, is a 3/16 in diameter hole. You could even ask, is this ventilated? Is this vented well enough to allow pressure equalization to occur? Even that's a little bit suspect. But again, it depends on how much you're expecting it to be pressure equalized. Some systems actually are really well ventilated and you can't even see it. So on the drawing on the left, it's a European panel system, and you can tell that because it doesn't show a water resistant barrier on the substructure. So I made a note of that. But the overhanging panel, the way it's bent, allows for a protected 12 millimeter half-inch vent opening that runs the entire length of every horizontal joint. That makes it a pretty well ventilated system. And it also means that very little water gets into it directly. It'll only be mistakes around windows and penetrations and stuff like that. Now, that same company provides an alternate detail shown on the right-hand side where you can actually bend the metal down and have exposed fastenings that actually make sure that there's no venting at all at the joint. But their blue arrows suggest that they want it to be ventilated, and that means that they're only letting the air in at details at the bottom and at the parapet. Whether they're letting it in at the windows, hard to tell. You have to look at the specific product. But really, if we're going to do ventilation, this is not vented enough. The weep holes are marginal in terms of getting enough airflow for most applications. And continuous slots are literally 100 times more ventilation effective than those weep holes. And so that means immediately you don't have to worry about the venting part of the equation. So again, this is showing a fiber cement system. The joints are, in this case, closed with profiles, usually aluminum and or EPDM or something like that. But they do show that there's ventilation at the bottom and the top. If you look at this, international manufacturer of pretty good quality products, they're showing that the air goes in at the bottom and out at the top through a perforated angle. They don't tell you how perforated. We don't know whether or not they've actually checked whether it gets blocked by dust and how much airflow goes through. But it is clear they only have it at the bottom of the top. And for a 4 or 5, 6-story building, that might not be enough. And so that's part of where the venting becomes more of an issue. And I'm showing here on the brick wall, commonly we are seeing people moving to open head joints. Depends where. There's still large parts of the United States where that's still not being done. And that's venting at the bottom only. So that unless they put those vents at the top, you don't have much ventilation. You put them at the top and it starts to matter. So if you're going to be making a product and want to specify it, you'll probably want to test it. And what we have in the ASTM is a specification for entangled meshes and polymeric dimple sheets. This test only tests from B to C. It doesn't include turning the corner and dealing with the vent openings. And so that has to be handled separately. So this standard was mostly built around a number of reports that we did almost 20 years ago now, where we looked at and developed these a pretty simple test technique of applying an air pressure, measuring the flow, and doing it over a range of pressures. Others have subsequently used this to measure airflow behind different types of products and systems. This is showing the flow on the left-hand side versus the pressure behind hardboard siding using either dimple sheets, mats, or 3/4 inch furring. And you can see the 3/4 inch furring strips does allow for a lot more airflow than the dimple sheet or the mesh. But what this doesn't tell you or answer is, so how much airflow do you need? And that goes back to what's your exposure? What's the materiality? What's the durability expectation? What's the rest of the wall assemblies? But at least this is, again, quantitatively, we can tell you how much airflow that system, that mesh, or whatever does. So the summary here is that vent openings are important. The flow of ventilation air is both because of vents and the gaps behind it. The larger gaps are more of an issue for being able to manage dimensional tolerances, avoiding things like fire rules and so on. But from a ventilation in practice, more often than not, it's the vents that are going to tell you how well the system works. So, a few more slides here. I just want to introduce the idea of pressure equalization. I frankly, we should be spending a whole session on pressure equalization if there's enough interest. But basically, it was a concept developed in the curtain wall industry to say, if we can make the pressure across the exterior aluminum of our joinery systems drop to zero, we won't have leakage because we'll be able to manage everything with laps and drainage. And so the concept here is to make sure that there's no wind gust pressures acting across the cladding, and that means that wind pressure will not drive water across cladding. Now, the other forces will still act, right? Gravity, the big one that causes leaks, is gravity. That's still getting the water in there, but it will, if this works, will work to eliminate air pressure driving water across the cladding. Now, a pressure equalized rain screen looks in many ways like a typical rain screen assembly, with one distinction, and that is these compartment separators. That's one of the key differentiators about how they make, how we talk about pressure equalization being different than ventilated. When we're dealing with pressure equalization, we are trying to minimize the effect of variable wind pressures over the facade. With ventilated systems, we like variable pressures over the facade because that's what drives air in one vent and out the other. With pressure equalization, the concern is we don't want to have too much variation, or we will end up with air dragging water into the cavity and around, particularly corners as shown here. So most designs that are claimed to be pressure equalized tend to have vents or drains only at the bottom. And if they do that, then they essentially have very limited to no ventilation. But actual evidence in wind tunnel studies and in the field, very limited as they are, there's only a few of each, have shown that actually distributing your vents around a panel actually helps pressure equalization as well. As well as making it possible to do ventilation well. So my last slide would say, remember, we don't always need ventilation, but it's almost always helpful. The amount of ventilation I need or really depends on what kind of claddings and exposure I have. And of course, moisture sensitive claddings or claddings that allow a lot of water through benefit the most. And when we're looking at how much ventilation we are going to design into a system, the vent openings and the gap have to be considered with equal weight. It's no use having a 2-inch gap with little holes that feed that gap. The limit will be the little holes. And likewise, there's no sense having a continuous 3/4 inch gap if it enters onto a 1/8 inch airspace. So, and as always, drainage and water resistive barriers, flashings, and weep holes are the first and most important thing to consider. Ventilation is really an add-on. And we require those water resistive barriers, right? The WRBs from the code, at least we do on this side of the Atlantic. And if you want to know about them, you're going to pay attention to Graham's session, which is the next one on December 6th. Pay attention to the RAINA website, LinkedIn, and all those places to capture his presentation, where you hopefully will get a lot to learn about. And if you've missed the previous ones, oh, sorry to hear that. Terrible for you. But if you go to the RAINA website or the RDH Learn Building Science site, you can find the downloads. You can review the introduction and drainage or rain screen walls. So with that, I'm going to turn it over to Todd. And Todd, you can riddle me with questions.
Yes, thank you, John, and thank you for a great presentation. I think the quantity and in kind of intensity of the question speaks to the value of the presentation. We've got a survey that just popped up. So I think everyone probably needs to fill out that survey. But I guess we'll start. I'll pick a few here, John. I'm sure you can kind of read through some of these as well. There was a question about NFPA 285 compliance, and I think you did address some of the fire requirements, the impact on fire that the ventilation and can have within a system. Is there a difference in the gap size of any concern in a vented versus ventilated cladding assemblies with regards to a potential negative impact on fire spread?
So let's just start with NFPA 285 is a specific test standard. And what's important, what you need to know is that it doesn't consider ventilation at all. Hopefully, the manufacturers who are submitting, the proponents who are submitting this system for NFPA testing are considering ventilation, because you want to test a system that is ventilated if your system needs it. And the challenge would be that if you have a large cavity, it makes it harder to pass 285. But you don't need a large cavity to have a ventilated system. So, but what you do need is you need weep holes and openings. And so one of the key details in an FPA 285 test is, how do you handle the head of the window? The flame is shooting out the window. How do you limit fire entry to that cavity? A lot of systems, they have a piece of steel there. And so the vents are on the front face. You need to make sure that the vents are realistic and appropriate. And when you're designing the test specimen or the test article, you want to make sure that they have realistic and effective ventilation systems, because you can't add them later.
Thank you. Another question was about, what dictates the location of the through wall flashing and the cavity closures, and does exterior insulation, I guess it could play a role, but does that play a role in that discussion as well?
I would say that the location of the flashings and compartment separators usually have almost nothing to do with the continuous insulation. And that's because we can make the flashing go through that continuous insulation without too much effort. With flashings, we're often putting them on a per floor basis, both to help with fire separation between floors, but also because we're having to deal with the most amount of differential movement at that location. And so it's almost it's a very convenient spot to accommodate sagging slabs and creeping columns at every floor line, and therefore you combine that with flashing. But there's no direct connection. Like you can, as you see in some of the European drawings, you can have a cavity that goes 4 stories high. As long as it passes the fire code, you have other ways of managing sagging and movement. You don't need the flashing. Compartmental separators are different in that they need to be located more near the edges of the building, because that's where the air pressure variations are greater. They don't need to be perfectly tight. They don't even need to be watertight. But and that's why we often see them at corners or integrated in the edges of the panel.
Well, I would eventually just go back to the continuous insulation, and I don't want to assume the gentleman's inquiry, but obviously with the energy codes kind of pushing more towards full CI, that having flashings, let's say at every floor slab, could impact the thermal performance of the enclosure. So there might be more of a push to not have those flashings over multiple stories.
Correct, Todd, but you're also, we're seeing, that's why I mentioned the fire and the movement. So I think that you have to address that carefully. That's a pretty significant change in building practice, and be careful that you don't run into unintended consequences. What you really are telling me, Todd, is you want a flashing, a cross-cavity flashing that doesn't have a big thermal impact while still having good fire resistance.
That's right.
And I don't know what that is. Really thin stainless steel, but if it's really thin, it starts to have problems with fire. So that is where we haven't got good solutions. We can talk about intumescence and all the rest, but that is where we can't say that we're getting rid of those flashings. That might be a path. It might also be a path that we use thermally effective and fire resistant flashings.
Have you seen a movement towards membrane flashings that transition to metal flashings?
Well, we've been doing that for a long time, so I haven't seen a move that way. That's because that's how you handle dimensional tolerances on the job site. But that's exactly what's taught us about the limitations of membrane flashings, because they don't have the fire resistance. And if they ask them to span much of a distance, they don't have the structural integrity to actually maintain their water tightness. So because they sag and they deform and so on.
Right.
So there's lots of industry experience, which is why there's some hybrid normally being used, membrane supported by metal.
Great. So another question came in. Does the warm air behind the cladding contain negative pressure or positive pressure?
So the air it doesn't contain pressure. It exists at a pressure, and that's just simply telling you how many molecules there are per cubic unit. So it tends to be at a lower pressure relative to outdoors because it expands, and therefore, because the more energetic molecules, they're hot, are knocking the neighbors further apart. There are fewer molecules per cubic container, but that means that they are lighter in weight, and so that means they rise, they float, and so they push out the top, and they get pulled in at the bottom. Basically, a chimney. But I don't think you should think of it as pressure being contained in the air. You should ask, what's the pressures? And that's why that equation is based on, for thermal buoyancy, it completely shows you how to calculate for any condition.
Question here from Jessica. So how does the wood finishing product influence diffusion rates? For example, a PU sealing product versus oil-based penetrating product.
Hugely. So a lot of the effort in finishing products for exterior is to make sure that the vapor permeance remains high, and therefore wood would allow water vapor to pass through. It's literally, how do I make it vapor permeable, and how do I make it UV resistant while remaining flexible? That's the holy grail. I'd say we have a lot of good coating products, but there's a lot of ones that aren't that good as well. So yeah, you do have to consider it. But ventilation is basically one way of not having to worry as much about that. Because if you can dry the back of your cladding and not rely on diffusion through it, then it means that you're less concerned with the vapor permeance of that coating, because you actually have another way of getting rid of the moisture.
Makes sense. And then she had a follow-up question about double strapping and if that reduces or improves the ventilation flow rate.
Essentially, always double strapping improves the ventilation flow rate, but it really depends. That's almost always the case. That's why we do double strapping. But it really, the question is, all you need is one layer, half an inch or something like that to 3/4 inch. All you need. The reason we do double strapping is because we can't even get that with a single layer. So you put horizontal strapping on, and now you don't have a good flow path from vent to vent. So you put double strapping
on. Denise had a question here about the heat energy, the point that you made about that, and whether or not the finished colors of the cladding would have an impact on the drying capacity of the cavity itself.
So the colors has a rather large effect on the temperature that cladding gets to. And as a consequence, let's say a bright white coated metal panel will not have as much ventilation than a dark black coated metal panel. So, and how much does that matter? It actually would matter a lot. It would really make a difference. But normally the way we do design is that we have enough safety factor, to use a term, that we're designing for not even full sun, right? We're thinking about the north side of a building with a beige coating, and we're designing for that. And as soon as you move around to the south or the west, or you have a darker color, well, you just have more airflow and it's less of an issue. And we see this forensically. I mean, when we're doing investigations of failed claddings because of moisture, you can absolutely see the difference on the orientation and the color on the ability for those systems to dry.
There's a question here from Cynthia with a project-specific question about a composite panel Rainscreen. It sounds like there's Z-girts that are filled with mineral wool, and then they're running vertically, and then having some horizontal hat channels that essentially interrupt the vertical airspace and would clearly restrict the air and the water from draining behind the panels. And would it make sense to provide a gap within the Z-girts that are running vertically to make sure that the water is draining freely and that you're getting that ventilation? Is that a solution that could work well?
I think the reason you're probably reading that is that I think that's actually kind of, although it's project specific, it's highly relevant. Now, the first thing I would say is don't use continuous Z-girts. I mean, that's just thermally disastrous. And so one should be using a clip and a rail. That being said, I have seen systems projects where the Z-girt or Z-girt, if you're north of the border, absolutely projects beyond the insulation layer, and they will have a bent out tab in the web of the Z to hold the insulation in place, and then buying them an extra half inch to 3/4 inch, whatever air gap, and then they attach their hat channels. But it also depends on the profile of the metal panel, because a lot of metal panels are mostly hollow, right? They have returns. And so it could be that you end up having a pretty reasonable airflow path around the horizontal hat along the backside of the void formed in that panel, if that makes sense to some of you.
Yeah.
So hard to talk without a pen and a board.
Here's maybe an easy one. Just you referenced open systems at the bottom. Fully open systems. What is the risk there with insects or vermin? Are we just talking a trade-off that yes, you're getting better ventilation and drainage, but obviously you have to still have some consideration? Or could you comment on that in terms of
absolutely? So I'm not sure I want to use the term vermin. It's politically loaded these days. But yes, you do want to keep insects out and rodents and small children and so on. But you probably, I just think that we need to consider that when we're designing our systems. Putting in a 3/8 inch diameter hole doesn't keep insects out. But it also is not that great for airflow. Whereas let's say a continuous slot of 3/8 inch has so much airflow that it wouldn't really be that big of a deal to put in screens to keep out insects and rodents and small children. So, and that's why, again, it's sort of like you need to design the vents with the whole system in mind. And that includes, I think that insects are a problem in a lot of places. Not really a problem, but a concern that we need to deal with. So I'm not by any means saying we shouldn't do it. I'm saying it should be designed, included in the concept of how much airflow you're going to get.
Joseph has a good question here about wildlife-urban interface and talking about ventilation in, kind of fire concern zones. Understanding that air carries tremendously more moisture than can diffuse, but the benefits of Rainscreen are oftentimes viewed as the Achilles heel of homes and firebrands. And I guess maybe the comment here that he had was, could we exchange the top vent? Could it be swapped for a highly vapor open diffusion port to kind of help with maybe embers and things like that, or what you could comment there?
So first of all, it's not necessarily, we haven't seen the evidence in testing that shows that the normal Rainscreen openings are that much of a problem. But it actually is totally connected, Todd, to the comment about insects. So one of the standard details for housing that we would use for insects in a rural area would be stainless steel mesh. Stainless steel mesh with an opening of under 1/16 of an inch would be a standard specification. And so if you use that kind of a material at the bottom of a Rainscreen, you're not getting burning brands that are going to go into your cavity. Now, you should also be at the top of the wall, you should be protecting that opening with metal flashing that comes down a little bit. And if you do both the bottom and the top like that, I mean, without having done the test, I'm saying I'm very confident you've dealt with burning brands. Now, that said, let's say that's not enough. Let's say the building code official thinks that burning brands are a 32nd of an inch, and they might find their way up. Well, then you can actually get intumescent strips, and you would put them at the bottom, not the top, so that in a fire, when the temperature builds up, those strips expand and block off that stainless steel screen completely. And that would be a way of being sure that you can, the fire official will say, yep, there's no entry point for, even though there will be air going in the cavity under those conditions, during high fire conditions, it'll plug her up.
A technical question here from Steve Gaynor, just regarding ASTM 2925. You mentioned it only measures from B to C, and was wondering if there was a complication with just moving the measuring equipment to the A and D marks to test that whole assembly.
There is no difficulty with doing that. It's really just a matter of the reason it's not there is that that's often not part of the system. So when you're doing a cladding system as opposed to a Rainscreen mesh product, that includes that vent opening, and it's a different scenario. And so to be more universal, it's just about this, the middle of the wall, basically. But it's totally the same approach, should work with a bit of care for whole systems. Absolutely. That's what we have recommended in the past.
And this is from Margaret Kinsella, and I have a feeling she might be asking this question from New York City. But could you speak to the ventilating walls that when they are also code requirements for fire blocking? So if there's fire blocking requirements, what are the best strategies there, I guess, that you've seen to ensure ventilation?
Well, you by saying that's New York, you throw a wrench in the works. So in the whole world outside of New York, fire blocking and ventilation isn't too much of a conflict, because fire blocking made of things like steel flashings and so on are considered normal. And so this is one of the reasons that goes back to every floor there is flashings, because it's also acting as fire blocking. Now, New York City, I really don't know what to say because I'm only just beginning to understand it, but they apparently are using different rules of physics, and I've seen no test data to support that they need to break it up more than that. But until we work out what they actually mean and why they mean it, I won't be able to give you a good answer on that. I mean, you can just follow the tests and just have very small ventilated claddings, meaning 4 foot by 4 foot square panels with ventilation top and bottom, and then fire stop, and then go on. That's not very realistic or practical or even necessary, but it would meet their requirements.
John Harris has a question here. Is there any consequence from putting the upper vents within a soffit cavity? So if, let's say, your vertical wall was terminating on a soffit.
Good question.
Yeah.
Good question, and I don't have a clear and definitive answer for that. In many cases, you would think that the soffit is well ventilated, and so really the fact that the cavity, the moisture in the wall cavity that enters into the soffit shouldn't be a problem because the soffit itself is highly ventilated. But that said, it would be nice if we didn't have to think about that. And but that means that you need to be willing then to have open slots or vents visible below the soffit. So I do think it does depend on the situation. And if you are going to vent a cavity into the soffit, if it's not a very wet cavity, meaning it doesn't have masonry or stucco over it, and you ventilate the soffit well, you should be okay. But again, it is kind of project specific. I'm trying to give you the parameters that you should be considering to make that decision.
There's a follow-up there. I thought venting from wall into soffit. Let's see. Hold on here.
Oh, I see, Sandy.
Yeah.
Oh, it depends where you are, right? The code is when you use, especially when you use capital C, that's a law made by man in a very specific area of the planet, and it changes with time and where you are on the planet. I'm talking about how it actually works. And in some places that's allowed by code. In some places it's not. It's true.
And Kyle, before Sandy asked about speaking towards venting a Rainscreen into a vented attic.
It's the same kind of a question, although I think it's more challenging to say yes to that because, again, it's not necessarily as well ventilated as even a soffit would be, right? So, but from a physics point of view, again, if you're using like, I don't know, metal cladding or fiber cement, something that doesn't store a lot of moisture and therefore doesn't put a lot of moisture into that cavity, it's probably going to be just fine. Yeah, there are other issues though, like again, other connectivities of fire, insects, and so on that might be limiting you to make that decision.
Okay. There's a few more here, John. Are we good to keep going, or what's? I know we're 20 minutes past.
Well, I'm okay.
All right. There was a question. You indicated that ventilation does not cool down the wall, but does a 25 millimeter uninterrupted airspace help exhaust the heat transfer?
No. So, but when I'm saying that the ventilation of a wall doesn't really do much in terms of heat, I'm thinking of a 25 millimeter cavity, or maybe even I would say probably more like a 2-inch 50 millimeter cavity, because that would be the kind of cavity you'd think about. Um, it has little effect, and in fact, the 50 millimeter ventilated cavity actually provides insulation value to the wall. So if it's not being heated by the sun, if you're talking about a cool evening, it still provides insulation value. That's a question I didn't get to, but sometimes people go, oh, if I ventilate, do I lose all my R value? Nope, not according to physical measurements. But there are some standards where they say, oh, you can't account for it. But that doesn't mean that's the answer. The real answer is that it still provides some R value. And that 50 millimeter cavity, even if pretty well ventilated, doesn't do much for cooling the wall under those intense sun conditions where you might want to cool it the most. And I'm talking about systems where you will have like a 6-inch cladding with a 1/2-inch gap, 6-inch cladding, and you put that on a 2-inch space. There you can measure a temperature difference, a drop, but it's not a lot. Things like color matter a lot more.
Right. And I guess there's just as a follow-up question of my own to that is, have you seen, ventilation and drainage be placed between the exterior insulation and the inner layer of the Rainscreen? And what are your comments on that?
Okay, that is a crazy question. That's not that crazy. The most common practical example of what you're describing, Todd, is that you will have an EIFS, synthetic stucco, where you're putting the lamina directly onto either stone wool or EPS type insulation. And you do that because you need the insulation providing some structural strength to that lamina. They put that over a gap to provide drainage. Not all the time, but a lot of times. That gap isn't ventilated. In fact, right now, best practice is that you should not ventilate it. You should make sure it's very carefully air sealed at the top, and the openings at the bottom should only be enough to allow drainage of water out. So I have measured in the field, and by the field, it's actually the field out my window. We built a little building. We used vented eaves and drained and only eaves. And we tried to capture the effect of wind blowing in that cavity. And you could, if you left it open at the top and had a 1/4-inch gap, you can start to measure it, but it's not as big as you might think. Which is why the recommendation, I think, made in the Canadian National Code is that it be limited to 1/8 of an inch, 3 millimeters, and be sealed at the top. And I would say we can be quite confident that that'll be on the safe side. If you seal it at the top, have an 1/8 of an inch, but you aren't getting ventilation, and that's key, right? So that has nothing to do with this seminar. It has to do with the previous seminar, Todd. Where were you then to ask that question?
All right. Does an open joint cladding have a negative impact on ventilation by reducing the temperature gradient within the cavity? You had said that the pressure caused by the temperature difference is predictable and reliable, but it seems to be that diffuse ventilation might reduce the temperature and therefore the pressure.
So I understand the question. And the short answer is no. And the reason it's no is that you are correct that there is less of the chimney effect acting because you're interrupting it more often with these openings. But the practical reality is that you're so increasing the amount of opening area that you do get an actual net increase in airflow. And it's also a more uniformly distributed airflow. It also works better in the wind. So because the wind is not as predictable as the sun, is blowing in all kinds of different angles, the open joint also tends to work better there. So it's true that it doesn't have as strong a chimney, but because of the increased vent area, it tends to be it's essentially always better ventilated. But it's a totally interesting question.
There's a few more here that I'm trying to read through, and I'm not sure I fully absorb. So I don't know if you're welcome to kind of read through these to see if there's anything that offhand you think would be
It's interesting. I haven't seen other ones. If you have open joints in masonry, um, so if you put open joints in masonry and not open head joints, is that creating an opportunity for infiltration? The whole concept of rain screen walls is that you have an air barrier that's independent. And the amount of air venting that we provide in modern rain screen walls, even if it's just a drain, not a drain and a vent at the top, is already so open that you're completely at the air tightness is completely dependent on the quality of your air barrier. And so there is really no practical trade-off between how much venting you have in the cladding and tolerance of your air barrier. We're well past the age of relying for the cladding to provide anything beyond a couple percent of the total air pressure drop across a wall system. It really is all about the air barrier. Existing buildings might have different things to deal with. Like if you're dealing with a 1970s bungalow and you're trying to do retrofits, then you have to keep that in mind. I'm just looking at if there's other ones. I don't see a lot of other ones.
Yeah, no, we're pretty close there.
So you see another one, but well, so maybe we will call it for the day then.
I think that's good. And you know, I personally want to thank everyone for attending on behalf of the Rainscreen Association. I think as John mentioned, this is going to be recorded. So if you guys need to reference it again or certainly share it with your colleagues, it will be posted both on the RAINA website as well as the RDH website. So, you know, if you can't find it, you can reach out to us as the organizers and we can help get that in your hands. And then, yeah, plugging away for the December program on the inner layer, the last
only
line
3
of
weeks,
defense.
and you know, WRB is a big deal. So Graham's got a lot of heavy lifting to do. So be there or be square.
There you go. All right. Thank you again, John and RDH for putting all this together. It's terrific.
All right. Great to see you all. Till next time.
Take care.